I am Matsushita from the Center for the Promotion of Excellence in Higher Education, Kyoto University. And I would like to be brief in my debate. The topic I chose is changing college science education, which three other lecturers spoke about. And I would like to discuss with you who should change what in what manner or how. Now, I have been involved in this presentation program, and in 2007, we had an international convention in Sydney for the college education, and there I listened to Dr. Wyman's presentation, and I thought that his expertise, specialties is cognitive psychology, but I was surprised to find out that he is a Nobel Prize laureate. I really wanted to invite Dr. Wyman and think about the scientific education together with him, and that was the start of my preparation for today's program. That's the theme. The theme is the future of the science education at undergraduate level. Now, the big theme topic today in Japan is the reform of the education at undergraduate level. And actually, in our center, CPEHE, I can point out two important points. One is that to position education based upon what students are learning and conduct reform on education. And another key point is the communication and networking between faculty and between universities. And for these 2 points, Professor Wyman have made a variety of lectures, and I would like to really learn from him and try to explore the answers for these 2 points. Well, Mr. President of Kyoto University is not here anymore, and that's a pity for me. But Dr. Wyman talked very important points for Kyoto University. In his presentation slide, he talked about this kind of thing. A necessary condition for changing college education is changing the teaching of science at the major research universities, because they set the norms that pervade the education system regarding how science is taught and what it means to learn science. And this is an excerpt from the science magazine called Change. And actually, Kyoto University trying to change the science education in Japan. This is the role that Kyoto University have to play. And I think this is a very important comment and insight by Professor Wyman. 3 lecturers today are wonderful professors. And of course, there are many other wonderful and excellent teachers who provide a scientific education. They are scattered as dots now. We have to connect them and provide network. And networking, I think, is something that our center, CPEHE, have to do. Then in doing so, how should we change? Now, in the presentation of Dr. Wyman, in the latter half of his presentation, he introduced how he carries out his class. And I had the same comment when I listened to his presentation in 2007. But in Japan, we have the hypothesis experiment class. This was established in 1960s and is conducted till today. The hypothesis experiment class is mainly done in elementary school and junior high schools, and with one class having 30 to 40 students. We provide a problem and then let students do prediction by raising hands. And since we will hear many different predictions, we will conduct discussions by the entire class, and students may change prediction, and then finally do experiment by a teacher. And repeat this to let students understand the important concept of science. Now, this is quite similar to a presentation by Dr. Wyman, but Dr. Wyman's class is about 200 students. So assignment, problem, prediction, discussion, and prediction change and experiment. And there was some difference from hypothesis experiment class that is use the technology, like using the clickers. And with the large number of students, so he forms a consensus group or small group for discussion. And another change is the assignment and follow-up. Now, I summarized in this presentation that Dr. Wyman's model is designed for large class. And assignment, I was surprised to listen to his presentation, but several times of the hours is required to do the assignment. And the follow-up is thoroughly done. This is, I believe, another features of Dr. Wyman's class. Now, the issue 1. The students' involvement and engagement, and how should we design such active learning by students? And 3 lecturers made points. When I think of the differences between Japan, Europe, and America, Japanese students spend less time outside class in studying. Another difference, well, earlier it was mentioned that the number of courses taken in one semester is very high. But in America, one course consists of lecture, tutorial, and experiment, and you may have 3 classes a week. But in Japan, you have only 1 class a week, having 1.5 hours long. So after 1 week, you forget most of the lectures you heard the previous week. And the lecture and tutorial and experiment are separate courses and classes. And this is the difference. And how should we consider this point is number 1. And number 2 is related to Professor Sasao and as well as Professor Bando's presentation. What is the strengths and weaknesses of performing experiments using simulation with the advancement of computer graphics? The students can understand simulation looking at computer graphics, but do not understand in real lives. Dr. Bando talked about metaphor. And this, I think, can be one problem of providing science education. Now, Dr. Wyman provides mainly the hypothetical experiments, but what about other variations in teaching, not using hypothetical experiments? We can compare this with Professor Bando's presentation. The second issue is thinking about what to change. Mainly educational context, content, and the curriculum. The target of each practice and the target students or the aim of a class of each practice. Professor Wyman is targeted at introductory physics, mainly a freshman and junior years, and Professor Bando is targeted at general education for humanities students, and Professor Sasao is targeted at, I don't know what grade of students he is targeted at, but introductory and specialized education for science students. Now, today, rather than looking at the differences, we should pay more attention to similarities. Not only in knowledge, but also thinking and beliefs have to be taught to students. Like understanding and thinking and feeling like a scientist. And this is something that we have to change. And what everybody said is that you have to try to understand, think, and feel like a scientist. And that this is very important. And I really understand this. But on the other hand, at the same time, the different target and different aim can change the educational content and curriculum. Now, issue 2, Professor Wyman's position here, and electric circuit example is a class from the humanities students, so maybe here. But at any rate, when we compare the novice and expert, we have to try to let students shift from novice side to expert side. And whereas Professor Bando is not trying to create a scientific expert, but rather create informed citizen with high scientific literacy. And I think that to some point, these two lines are integrated, and after that, some point, they divided into two courses. Another question I especially would like to ask Dr. Wyman. He introduced a very introductory physics today, but the British Columbia University is a very well-known research university. And how do you lead this introductory physics to leading-edge physics? In Japan, the junior, senior high school students have a very relatively high literacy in science, but in college, they are caught up and surpassed by other students in other countries. But when leading students from introductory physics to leading-edge physics, what Professor Wyman place importance and emphasis upon? This is something that I would like to hear from him. Now, the third point, thinking about who is going to change the science education. As the president said at the opening of the program, and also three lecturers are the excellent researchers as well as the excellent educators. Now, the coexistence of education and research is quite difficult, and I'm sure that we are all troubled by this. And I think that there is a limit of effort and abilities of individual teachers. And so I would like to think of three typical relationships of education and research. One is the shift of priorities in one's life cycle. And the second is division of role between faculties and teachers. And third is the duplication. And I think that these are three typical relationships between education and research. And number one is the shift of priorities in one's life cycle. In other words, when you are young, you mainly focus on research. But when you, at some point in time, quite successful in your research, and then you pay attention more to education. And the career path of PhDs in science and the research can be conducted outside college, like science communication, and people also start to get involved in elementary and secondary education. And the second point, which is not advanced in Japan yet, is the division of roles. In other words, among university teachers, research-focused teachers and education-focused teachers can be divided or categorized in even in one university. And also another division of roles between teachers and specialists, such as instructional designer and other specialists. They have a lot in America, but not many in Japan. This gives more burden to teachers in Japan. Thirdly, division of roles between human and technology. When you conduct simulation experiments, for example, this reduces the burden on human. And thirdly, duplication. As I believe that Professor Wyman does this, actually, this is implementing education like research. In other words, implementing science education as a science. Not only physics, but cognitive psychology and brain research can be used as tools. By so doing, Professor Wyman, implements science education as a science. Now, in the introduction of Professor Wyman, it was mentioned that Carnegie Foundation for the Advancement of Teaching provides a scholarship of teaching and learning. And not only research, but also teaching and learning receives emphasis. And these three aspects, all of them have to be pursued. And this can be one type of a duplication, but this is quite difficult at the same time. Now, another a relationship between education and research from a different angle when we think that who should change this. Now, building networks and communities is one important aspect. Now, Professor Wyman talked this very briefly, introduced PhET very briefly. Sorry, the slide is old. Now, this is the Assimilation experiments site. And I hear that he spent his Nobel Prize money to create this page and the web site. But many people can use this assimilation experiments and design the class. And the problems, designing the problems and designing lesson plans can also be supported, and also it functions as the community of the practice. And Professor Bando joins the NPO, the Scientific Education Exchange Einstein, and this is a place that science teaching material and educational knowledge is provided. So issue 3. How to understand the relationship between education and research in each practice. How each presenter or instructor thinks about this relationship in their practice. And the second point, what kinds of networks and communities support educational reform effectively? What to share and who develops and maintains them? And maintaining is also important. So who should undertake this endeavor? I think we want to discuss these points. Thank you very much.
To have a panel discussions based upon mainly of the issues raised by Dr. Matsushita. So panelists, please come up to the podium. I would like to start with a debate or discussions. There are several questions already posed to Dr. Wyman. So, Dr. Wyman, could you respond first?
So please make quick. Okay, so my first comment is that there were many more than 7 things I was asked, and my brain doesn't hold many more than that. So I'll only cover a few that were struck me as. First, I want to say one comment that in response to Professor Bando, her example of having the students picture themselves as atoms and doing these experiments relating to that. And I think this is a very good idea, very effective. I've even used something like this myself, but I think you can also think about it in terms of the cognitive psychology aspects that I was talking about, in that this is first, it's dealing with students' prior knowledge and thinking. It's putting them things they understand about relations between themselves and people around them, and it's making an analogies. It's sort of relating how people interact to how atoms interact. So all of these things are doing, or these kinds of activities are doing exactly, are ways to implement these basic ideas that I was talking about. So I think that you can understand that and see why they'd be effective from that point of view. one thing I want to make a comment about, because there have been several comments, both in speakers and then audience, about the deficiencies of students nowadays and how they aren't as well prepared, they aren't as motivated, and so on as in the past. This is something which you can go back as long as we have writing. I think the earliest records are about 3,000 years old, where teachers say, oh, the students these days, they're not as motivated, they're not as well prepared, they don't work as hard as they did when we were students. And, you know, probably teachers were saying that more than 3,000 years ago, but we don't have writing back then. And it continues ever since. You can see, you know, you look at the record, and this is stated over and over and over again. And I think it's some sort of basic human psychology to see things, see people being different, and notice the things that were worse and not notice the parts that are better. For example, if you want to look at students nowadays, their ability to find information on subjects, their ability to communicate and share information is vastly beyond what any of us could do when we were students. But, you know, the teachers aren't there thinking about what they're better at, they're always thinking about what they're worse at. And so I just think it's important to recognize that, yes, students are always different from the previous generations. Society changes, but if they really were getting worse every generation, we wouldn't be progressing in the way society has. We wouldn't have science the way we do. And so I think it's important to focus not on the fact that they're worse, but just the fact that they're different, and how, as students change and their experiences change, how can we best take advantage of that to enhance how they learn, how they succeed, rather than just saying, no, it should be changed back how it used to be. Okay, there are just many other things. I agree with almost, most of what's been said. I guess I'll just make one quick comment. A couple of brief comments on the issue of simulations versus real life, and then the FAT website. First, a comment I should have said is that one of the things we've used the technology to do is make the site so it's translation friendly, and so in fact, many, if not all, of the simulations are now available, and the text is available in Japanese, and the ones that aren't can very quickly and easily be translated by anyone who knows both languages. So that's just a plug for that. But more importantly, the issue of learning with simulations versus real experiments, it's a complicated subject, and there's no clean and simple answer. We know that students can learn very well from real experiments. We also have lots of examples where students learn very little from doing real experiments. And the same is true for simulations. And so anything like, in any form, whether it's simulations, experiments, lecture, etc., you really have to do careful measurements, and that's what's critical. And in fact, the FET simulations that we do, we're confident they're pretty good. And the reason they're pretty good is because we tested them over and over and over. They weren't good often when we started. We find out, we measure it, and students don't learn what we want. They aren't able to take things from the simulations and understand the world around them. So we change the simulation, and we test it again, just like you do in science. And so now we know, yes, most of what are up there are pretty effective because we've tried it over and over until they work. And And so I think that's, one has to have that same spirit in almost anything we do in education. You've got to really carefully measure it for the students you have, the form of instruction you use. You've got to measure how well it really works, and you learn from that and improve from that, and that's how you keep getting better. So maybe that's enough.
Thank you very much.
Thank you. Thank you very much. I believe that there are three main comments, if I can wrap up. One is that, well, that experiment, real experiment or simulation, that Dr. Bando's version and simulation, well, that the technology can provide that the good benefit also. Number one is a less motivation among students. Well, this can be interpreted in one word of generation gap. Well, all those good old days is probably a human psychology. Good old days. Why should the old is always good? It's probably the psychology. Number three, that the simulation or the real experiment. Well, real experiment was the first point. Dr. Bando's trial is very, very interesting. And the simulation and experiment both has merits and demerits. So simulation or experiment, Dr. Bando, could you comment? Do you have additional comment? And Dr. Sasao also. Number one is what? That real experiment using the students as atoms. Let me start from the last question. Simulation. Simulation is a sort of pseudo reality. That the reality is difficult to test, and therefore to show that the pseudo reality by calculation. But my definition is a little different. Dr. Lang showed me that Dr. Wyman's example. My impression was, for example, there are a lot of particles in the air. Particles in, well, this is a cluster of atoms. Particles come in and how to mix. That was a simulation. Whether that the students can understand whether that mixing, how that the students can grab the idea of concept of mixing. Whether students without too much of the basic information, can they really, for example, that it's like the people coming into the trains. That simulation, what is the purpose of that simulation? Depending on the level of the students, what that simulation can really tell to the students, mixing. Or that the real experiment, sometimes that the real experiment using the student's body sometimes fail. But so long as that you have that the very clear purpose, what you want the student to learn from this, that is a core. So long as a teacher is very clear on this, it's up to them. That simulation or real experiment, or sometimes they have to modify, mix, or that scientifically that they have to evaluate in which case that which is better. I think this is something of the mission of the future as the science educator like ours. And another what? Another question is what? Motivation. The students with a low morale. My concern is that, my assumption, as Dr. Wyman says, that the current students are brought up in different culture. And what they fall short of our expectation in some areas, but other areas that the students are very good. I believe that was a gist of Dr. Wyman. You see that, for example, the computer, or that sometimes that I ask the students to learn how to make the program, software. And if the answer is correct, that the program says that very good. And the student says that not very good, but the sound. Sound counts, Dr. Bando, not the computer screen say that you are good. Your answer is good. So that they want to make the program visual with a sound, swishy and fancy things to praise them. But to me, well, it should be sufficient that your program says that your answer was correct. But no, the students expect much, much more swishy and zip and the letters zip and zap and the music. But if that is their wish, that is attraction, we have to recognize, well, if you consider that the students cannot react in the way you like, I don't think that it is unfair to say such students are bad students or lowly motivated students. That's, well, the time changed. This is something that we have to consider more carefully into the future. That information literacy, computer literacy, the student comes in a very different levels, and the computer literacy, the level expected change from 1 year to the year. And so, as Dr. Wyman, you have to check that the entry level and have to adjust your teaching method. Otherwise, that you cannot get the best result out of the teaching. Was there one more? Let me respond. First, generation gap. Okay, let me start with answering this point. As Dr. Wyman says, as the writing started, yes, there are always the people says that the youngsters of the current youngsters are nonsense. They are lazy. They are very bad students. Well, that has been constantly said, generation after generation. Yes, that when there was the issue of that science haters appeared in the societies, that I said that, it was deplorable, and I just gave up. But I have changed because that the youngsters, it's not the issue of the youngsters. There's nothing wrong with them. If there's something wrong with this, our generation, the people of our age are, well, there's something with us, not them. Having said so, how shall we cope with this? The changing of the liking and the preference of the students. If we cannot cope with this, the consequence will be serious. That is also the fact. You see that, you see that it is always the case, and we cannot do anything about it. And we cannot keep it as it is, saying that it's the generation gap, it always existed. We have to do something about it. Well, how to motivate the students? There are many ways of motivating the students. Get the students excited. Well, that the students sometimes jump at them and with the shiny eyes, and that would be very rewarding time. And there are possible, and I believe there are many, it is possible. Having said so, considering that the university as a whole, as an educational system as a whole, as Japan as a whole, is there a general answer or panacea? Probably not. It is not as simple as that.
And the second issue, that is an assimilation versus a real experiment, which is better. So of course, and there is no clear answer. It depends upon the situation. It depends upon who is the audience. But which is missing from the current students, so that they don't have many experience of the touching upon the real things. So we have to provide the students with the more opportunities to do the real experiments. And I think this is a challenge for Japan. This is applicable not only for the higher education, but also to the elementary and the secondary education. How to give students more opportunities of the real experiments. So I think this is suitable for Japan. So Dr. Wyman, do you have any additional comments after listening to the comments from the other panelists?
Okay. The one thing I might comment following on their remarks, and also on Dr. Matsushita's comment about how do you deal with the problem that students in Japan, actually other places as well, but it's particularly dramatic in Japan, seem to do very well in these in mastery of content and so on, and good at lower grade levels, but then seem to lose interest or relatively not wanting to go into science and pursue science. There's some research that my group has done recently that's really quite striking, which is that we studied these perceptions of science by students, and we found that if we measure students' perceptions about science when they first come to the university, so this is their first week of being at the university, their perceptions are a much better predictor of whether they're going to be a successful student in physics 3 or 4 years later than actually their grades on their first year physics courses. And so just so you can understand what I'm saying here, I'm saying that on their first day, we can look at their perceptions and make a much more accurate prediction based on that than after you've had them in physics classes for 6 months and measure how they're doing in their physics classes. So what that tells you is that these perceptions, if you're worried about who's going to go into science and having their interest in science, you need to worry much more about their perceptions about science than you do about actually teaching them the content of science. And so what do we know about what shapes these perceptions? Well, not nearly as much as we'd like, but as I mentioned in my talk, what we have seen is most of the formal school experience actually has a negative impact. And so the students who appear to come in with quite expert perceptions of science, and therefore they seem to do well, they stay, they go on to become scientists, most of that seems to be shaped by informal experiences, relatives, neighbors who are in science and talk to them about science that way. Sometimes we see it's very, it can be a teacher at, the grade 9, grade 10, a particularly special science teacher who's taken a particular interest and connected up with that student and gives them a view about what science is and what it can be that's quite different than they're getting from their formal school experience. And that seems to be shaping these things, getting these kind of results, outcomes that we'd like to see. And so I think what educators need to do is think much more about, it's really more about the human psychology that goes into these things, and worry about dealing with those more in our science classes than being sure that we cover lots of content and making sure they can score very high on these formal exams. I think in the end, as we saw so convincingly, that can turn out to not be so useful.